Hello everyone. Today we will be doing matrix algebra. In matrix algebra, the most important tool is a matrix. Now matrices are used a lot in a wide variety of applications. It is used in page ranking algorithms, which we find a lot when we do Google search, helps in encryption of messages of codes, finding the best possible solution in our economy, which is basically applying the relatives input-output problems, balancing a chemical equation, solving the study of the flow of networks in engineering, social sciences, physical sciences, and as simple as animated movies. So let's go ahead and look at what are the topics we will be doing in this session. We will be looking at what is a matrix, types of matrices, and 4 operations on matrices: addition, subtraction, scalar multiplication, and multiplication of matrices. So let's begin with what is a matrix? Matrix is very simple. It's a rectangular arrangement of elements in horizontal rows and vertical columns. We denote a matrix by a capital letter. The entries of the matrix are called elements, and we represent the lowercase elements of these matrices by lowercase letters. So it's very simple. You can think of that like you have a rectangular, so you have say 3 rows, and you have say 4 columns. So you can have, and then what you do is when you write a matrix, what we can do is by convention, we just put some brackets and say, hey, these 3 rows and it has 4 columns. And we represent a matrix, it's all convention, say by a capital letter, say K. And these elements here can be A, B, C, I can make a star, I can have a check mark, but the convention is using lowercase letters to do it. It doesn't matter what you want these elements to be. But the most important part in a matrix is the position of each of these elements we are having in it. So let's look at some examples of matrices. Now, the first matrix is capital A. It has 3 rows and 1 column. Matrix B has 1 row but 3 columns. And the elements inside matrix B here is the first element is a 2. The element in the first row, the second column is -5, and the last column and the first row is 7 in B. So as I said, position matters a lot. Okay. Then let's look at C. We have 2 rows, 2 columns. D has 2 rows but 3 columns. Now let's look at E. E is having 3 rows and 3 columns. Similarly, O, subscript 3. Now these names are very specifically I have written down, and even I, subscript 3. I3 or O3, they are very specific names. You'll be seeing them in a few minutes. And then capital O is just a bunch of zeros. Now, these are some examples. I will be referring them later on too. So let's talk about these examples and some more concepts here. The first concept is the size of the matrix. The size of the matrix is very important. It is defined by how many rows and how many columns it has. And we always write the size of the matrix, say there are m rows and n columns, we say m by n. Very important, guys, this multiplication sign is always represented in the matrix world by the word by. It means m rows, a matrix has an n columns. Now let's go back to the previous slide. I'm going to look at all the sizes of these various matrices we had. Okay, let's start with A. It has how many rows? 3 rows, 1 column. The convention is we always write the number of rows first, and then we write down the number of columns. So this is 3 rows and 1 column. So we say 3 by 1. Now matrix B has 1 row but 3 columns. So we write as 1 by 3. Matrix C has 2 rows and 2 columns. Now D has 2 rows and 3 columns. Matrix E has 3 rows and 3 columns. It doesn't matter, guys, if I write the size on the top next to it. I'm just using a convention to make my life simple. O3 is a bunch of zeros, but it has 3 rows and 3 columns. Similarly, this O is also a bunch of zeros, but this one has 2 rows and 3 columns. I3, on the other hand, also has 3 rows and 3 columns. Now, we have learned about the sizes of the matrices. So let's look at some more concepts. The types of matrices. And the types of matrices, they are written down on slide 6, but I'll be explaining them with the help of these examples. So the first type is a type called the column matrix. Okay, so we say, what is a column matrix? A column matrix or a column vector. It is a matrix which has only 1 column. So A is a column matrix. B, on the other hand, has only 1 row. So B is a row matrix. A matrix which has only 1 row is called a row matrix. Or if you remember your physics, it's a row vector, and A is a column vector. Now, let's look at C. C has same number of rows and same number of columns. So just using the fact in a geometry, a square has all the sides same, so we call C to be a square matrix, because the number of rows and the number of columns are the same. So following the same analysis, we say, hey, D doesn't have the same number of rows and columns, so we say, hey, D is a rectangular matrix. Okay. Now E, notice, has the same number of rows and columns, so E is also a square matrix. O3 is also a square matrix. And I3 also is a square matrix, whereas the capital O is a rectangular matrix. But these two matrices, O3 and O, are very important because every element is 0. So what do we have over here in O3 and O? These are called zero matrices. Now specifically O3 I have written is to show if you have the number of rows and number of columns to be the same, then we kind of use the convention O3, depending upon how many rows and columns. So you just have to write it once. And then I3 is also on the same one. We have 3 rows, 3 columns, so I3. Now the difference between O3 and I3 is that in I3, the diagonal elements, which we convention we start from top left and go down, all the diagonal elements are 1. So this has a specific name called an identity matrix. Okay. On that same scenario, we say O3 is a zero matrix. So if you see a zero matrix, it is basically saying every element inside is a 0, and even O is a zero matrix. The only difference between O3 and O is that one is a rectangular, the other is a square. Okay. Now, E is a square matrix, but now there are some very specific things also to keep in mind. Whenever you have a square matrix, and if the non-diagonal elements, now remember the convention we are going to be following is this. The convention is that the diagonal elements which we are going to be considering is the elements which are starting from the top left and going down right. So these ones starting top left to down right, these are diagonal elements. And every other element is a non-diagonal element. Now, if you have a matrix where every non-diagonal element is a 0, then we say that this matrix is also called a diagonal matrix. The reason is that every non-diagonal element, notice this, is a 0. Every non-diagonal element is a 0. So in that sense, O3 also is a diagonal matrix, because every element is a 0, so it doesn't matter, but it is a diagonal matrix because every non-diagonal entry is a 0. We don't care what is the diagonal entries, but we're only caring all the non-diagonal elements is 0. Now, when we come to I3, as I said, it's a very specific name and we'll be using this a lot. This is the one where you have the identity matrix. The reason is that not only every non-diagonal element is a 0, but every diagonal element is a 1. So I3 is a very, very special matrix, remember. This is, as the name suggests, I, that's an identity. That means every diagonal element is 1. And the subscript basically says, hey, it's a matrix of size 3 by 3. Now, all these, what we have just talked about in the slide, is written down in slides number 6 and 7 below. So here it is, a matrix with one column, a row matrix, a rectangular matrix, square matrices, diagonal matrices, an identity matrix, and a 0 matrix. So these are the very, very specific matrices we will be talking a lot throughout. So this was like some specifics. So let's talk about a general matrix. So what is a general matrix? A general matrix is a matrix of size m by n. That means we are just becoming very abstract here. We do not know how many rows. We're not putting in some numbers. We're simply saying, hey, I have a matrix with size m by n. That means I have m rows and n columns, okay? And then also we talk about how will we write the elements. So it's a convention we're doing so that it will help us out, is that when we write down a general matrix, the elements in the general matrix give us the idea where that element is. So it will always have a double script. And what we do is, if this is the first element and the first column, so we write A11. Then we can have, so let me just write it down over here, simply 1 here. So if it is A11. So A11 says that I have an element in the first row, first column, making simple. Then we write the next element as A12. That means first row, second column. And then suppose we have a jth column, so we write A1j. That means this element, A1j, by the subscript we can tell what is the position of the element in that matrix, the first row, the jth column. As we have n columns, we write A1n. Similarly, we can say second row. So second row is A21, A22, and then there will be element A2j, and going forward A2n. Okay, then because we're going to write this matrix in a very simplest form and it's very concise form too. So we say, hey, there's an ith row. These are all conventions, guys, keep in mind. So I have an ith row, which is AI1, AI2, dot, 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 AIJ. So this is AIJ is a very important, because this is like representing, we'll represent the whole matrix by that. Later on, I will just show you. So then AIN, and then it has m rows. So that would be the last row, AM1, just we can see it over here, AM2, then AMJ, and AMN. Okay. Notice the diagonal elements also are very, very amazing here too. The first We remember we start from top left and the bottom right. So A11, A22. In a diagonal elements, the number of rows and the subscript will have the same value. 1, 1, 2, 2, 3, 3, 4, 4, and stuff like that. Okay. Now, sometimes we don't want to write this for every element. What we do is, we write this as A, I, J, where I varies from 1 to M and J varies from 1 to N. Now, let's look at this matrix again. We can represent, so because remember, every column, it has further rows in it. So we can represent is that the whole first row by A1. Now the jth column is represented by AJ and the last column is represented by AN. So we can write this matrix A also like this: A1, A2 up to AN. Now this A1 is representing column 1 which has M rows in it. A2 again is a column but it has again M rows. Similarly AN, the last row, has M columns. So we can identify this every column as a vector in Rm. Okay, so all this what I just talked about is written over here in the next slide. So this was just a general form about information about matrices. Let's do some operations on matrices. Okay. The very simplest operation, adding matrices. Okay, so if you want, so before adding, let's talk about matrices being equal. We say, hey, two matrices are equal. Now, two matrices, we say a matrix is going to be equal. Suppose this is an entry 1, 2, 3, 4, and I have another matrix, say 1, 2, 0, 1. Now, these two matrices look like the same. They're square matrices. But if I want to say it is equal, they can only be equal. Not only the sizes have to be the same, but every element also has to be the same. So this one, notice 1 is the same as 1, okay? The sizes are the same. First of all, it's a 2 by 2, a 2 by 2. Okay, we're good to go. And then then we look at every element. Equal means everything on the left-hand side should be mirroring everything on the right-hand side. So 2 and 2, that's also same. But this element is 3, that is the second row, first column, and there is a 0. Nope. These two are not the same. So that means these two matrices are not equal. So when we say two matrices are equal, it means they not only have the same sizes, but the corresponding elements at their respective positions in the matrices also have to be the same. Okay. So if A and B are M cross N matrices, then the sum of these two matrices is basically we add the corresponding columns or the corresponding entries in the appropriate position. So for example, if I have that matrix say 1, 2, minus 1, 0, I'm adding, so let's take an M 2 by 3 matrix. So I have 0 and 1, and I'm adding another matrix, say 3, 1, minus 2, 0, 0. So first of all, if I have to add two matrices, I have to make sure that the sizes are the same. So this is a 2 by 3. Again, this is also a 2 by 3. So clearly I can add, these matrices can be added because the sizes are the same. Now, when we add the corresponding. So 1 plus 3 will be 4. 2 plus 1, 3. 0 minus 1, minus 1. Minus 1, minus 2, second row, first column. 0 and 0, and 1 and 0, 1. Very simple. Adding of matrices is not a problem. Okay, so let's go ahead and do some examples here. We have a matrix A, B, C, and D. Before we do addition, so let's go ahead and look at the sizes. Matrix A is of size what? 2 by 3. B again 2 by 3. C is a 2 by 2. and D is a 2 by 2. Now let's add A and B. So when we add A and B, what are the elements we are going to get here? So this would be what, 5? Then we would have 1, 5 and 1, 6, minus 1 and 3, 2, 3 and 5, 8, 2 and 7, 9. Okay, let's look at A plus C. Okay, if I add 4 and 5, 0 and 2, but poor 5 has nowhere to go. So A plus C is not possible. Remember, the first important thing is the sizes have to be the same. I cannot add a 2 by 3 to a 2 by 2. So that's not possible. Let's do C plus D. Okay, both of them are sizes are the same. Yes, they're 2 by 2 matrices. That means they're square matrices. Good to go. Now let's do the math of adding these two. Remember, we're going to add the corresponding elements. 5 and 2, 7, 2. Now remember, the second column and the first row of C will be added to the second column and the first row of D. 2 minus 1, 1. 10 plus 1, 11. Minus 6 minus 11, minus 17. Very simple. Now let's look at scalar multiples. Now, if R is a scalar and A is a matrix, then a scalar multiple RA is the matrix whose columns are R times the corresponding columns in A. Very simple. You multiply R to every element inside the matrix. That's what it's simply a scalar multiple of a matrix means. So for example, if I want to find 2 times A, what would be it? It will be 8. 2 is going to be multiplied to every element inside this matrix. So 8, 0, 10, minus 2, 6, and 4. Now let's multiply minus B, minus 1 to B. What will we get? Minus 1, minus 1, minus 1, and then minus 3, minus 5, minus 7. Now if I add matrix 2A minus B, basically first we are doing scalar multiplication and then we are subtracting matrices. Or 2A minus B can be same also looked at as 2A plus minus B. It's basically adding two matrices where the scalar multiple to B is minus 1 and scalar multiple to A is a 2. So when you do the math, what do we get? 8 minus 1, 7, minus 1, 9, minus 2 minus 3, minus 5, 6 minus 5, 1, 4 minus 7, minus 3. Okay guys, for you guys to have some fun, go ahead and practice these problems. By the way, there is multiplication here. A little spelling mistake. Okay, now let's go ahead and look at some matrix properties. Remember, we will be using these properties. We are not going to prove them. Okay, so what are these matrix properties? If you have three matrices of the same size, and in other words, when we're going to apply these to these, the A, B's and A plus B and C's, the same size means depending upon whatever the matrix we have, if I want to add A to B, both of them should have the same size. Or if I'm adding A and B and C, the matrix addition should be possible. That's what it literally means here. So we have matrices of the same size, and R and S are scalars. So the very first property in this theorem says if I add A to B, it doesn't matter if I put A first or B first, it's the same. So this is called the commutative property. Okay, let's look at the next one. If I add three matrices A, B, and C, in the left-hand side, we are grouping A and B together, then we add C. It's the same answer as if I'm grouping B and C together and then add A. This is called the associative property. Okay, now when A is added This is a zero matrix, guys. It is not the number 0. This is a zero matrix. So if you add a matrix to a zero matrix, you get the matrix itself. So this zero matrix is called the additive identity. Now, if we multiply a scalar to sum of two matrices, it's the same as we are multiplying scalar to individual matrices and then we add that. Or if we are adding two scalars and then multiply it to a matrix, it's the same as we independently do this R, scalar multiplication to A and S to A and then add. So these two are our distributive properties. And finally, a scalar multiplied to a scalar with a matrix, or if we multiply the scalars first and then multiply to a matrix, it will still give us the same answer. So most important for us is just to be aware of these properties. We are not going to prove them. Okay. The main important thing is matrix multiplication. Now, when we want to multiply two matrices, a very, very important condition for that to take place. In matrix multiplication, the number of columns of the first matrix should be equal to the number of rows of the second matrix. So this matrix multiplication is going to give us a new matrix, provided this condition holds. This is the most important condition in matrix multiplication. What I'm going to do is, I will show you with the help of examples how matrix multiplication is done. Okay, let's start with that. Now, I have a matrix A. If you notice, this is a 3 by 1, okay, and a matrix B, which is of size 1 by 3. A, if you remember, is a column matrix and B is a row matrix. So if I want to multiply A with B, okay, let's look at this. Can I do A with B? For that to happen, the number of columns, according to the condition, the number of columns, because A is the first matrix, number of columns of the first matrix is the same as the number of rows. So these two are exactly the same. And hence, this matrix multiplication is possible. Not only that matrix multiplication is possible, but it also tells us the size of the matrix. The size of this matrix, suppose this is a new matrix C, is 3 by 3. In other words, this 3 is coming from here. The new matrix number of rows is exactly the same as the number of the rows of the first matrix. And the number of columns of this new matrix C is the same as the number of columns of the second matrix. Very important things to keep in mind. Okay, let's see if B times A is also possible. We said A times B. Let's look at BA. Now, B is what? 1 by 3, okay? So B is what? 1 by 3, and A is 3 by 1. Great. The number of rows, now here B is the first matrix. Number of columns of B is the same as number of rows of A. Yes, this matrix multiplication is also possible. And this new matrix will be of size. Now remember, what we do is the ones which are common here, you cancel out, it is a size 1 by 1. So what basically happened is the common part is cancelled out and we are left with 1 times 1 by 1, not times. Sorry. So this new matrix is of size 1 by 1. If you have a matrix AB, that is of size 3 by 3. Okay, so now we just have made sure that this matrix multiplication is possible. Now we would like to go and see how can we do it and what are the elements of the new matrix we have created. Okay, let's start with B times A. Okay, let's look at B times A. A is the matrix 1, 9, 4. B is the matrix 2, minus 5, 7. So the first thing we do is we write these matrices as they're given and as the order they are coming in. Now we know B times A is possible, and this new matrix, say D, is of the size 1 by 1. Because remember, what is B? B is the matrix of size 1 by 3. A is the matrix of size 3 by 1. So clearly, what would be the new matrix BA? You basically remove the 3 and 3 here. Okay, and you're left with 1 and 1. So 1 row, 1 column. In other words, it's just one number. But how do we do it? This one, to do this matrix elements, what we do is we look at, now remember, what is this one? We look at the first element in the matrix B and multiply it with the first element of the matrix A. So 2 is multiplied to 1. That's what we have. And then we have a plus in between. We multiply minus 5 with 9. And then the last one is 7 with 4. So you multiply 7 with 4, 9 with minus 5, and then you have a plus sign in between. So what do you get? A 2 minus 45 plus 28. The final answer, negative 15. Okay. Now this was B times A. How would we get the elements of A times B? Let's look at that. So we're going to look at the matrix A with B. Once again, A is of size 3 by 1. B is of size 1 by 3. Now the new matrix AB, we all know, is going to be a size 3 by 3. That means 3 rows and 3 columns. Okay. What we normally do is this. I'm going to actually show you how to work on this. Now, it's a 3 by 3. So what I literally do is I write down a general form of this matrix in terms of the subscripts, which is going to make my life very simple here. Okay. So this will be C11. I'm just writing down any element. You can have K, whatever you guys like. It does not matter. But I'm making sure that I'm writing down the correct subscripts. C12, C13, C21, C22, C23, C31, C32, C33. Remember, when you multiply A with B, you get a new matrix C, which is of 3 by 3 size. 3 by 3 size means 3 rows and 3 columns. And it is much more better to write it in the form of the general matrix with the subscripts of every element. Now, when I want to write down the elements, so C11, let's look at C11. This element, C11, means you multiply. So this is how you look at C11 means you go to the first matrix, look at the first element. And you go to the second matrix, you look at the second, and this one is going to, the C1, the second subscript is representing the columns. Remember that. First subscript represents the rows of the first matrix, and the second subscript of the element represents the element in the first column. Okay, so this is going to be 1 by 2. So C11 means first 1 by 2. It's 1 times 2. Now this is 1 times 2 here. It is by. This means size, whereas this means multiplication. 1 times 2 is 2. Let's look at the element C12. Now, the subscript is going to give me all the information. This means the first row and the first element here. That's 1. Now, 2 means you go to the second column and the element which appears in the second column of this matrix B. And that's the first column you're looking at. So it is -5. So you have -5. Similarly, C13 is 1 by 7. Okay, let's pick up, say, C23. That means C2 means you go to the first matrix, look at the second row. Second row is 9. So this one is 9. Now this is multiplication times. Now this 3 means you go to the second matrix and look at the third column. Second matrix, third column is a 7. So C23 is the element 63, and that's where it is. Okay, and so the rest of the terms I've written down 4 by 2, 4 minus 5. So this, remember guys, is multiplication. And when you write by convention, if you write a capital letter and then as a subscript 3 cross 3, that means 3 by 3. I'm talking over here is a size. Okay, so this one, you've already got the matrix AB. Now this was because a one row matrix multiplied to a column matrix or a row matrix. But we will have matrices where we will have more than 1 rows and 1 columns. And how do we do that? Okay, so let's look at this one. I would like to find the matrix AB. In order to do that, I have the very first condition is the number of columns of A the same as the number of rows of B? If that's fine, only then AB matrix multiplication is possible. Let's look at A. A is a matrix of size 2 by 2. B is a matrix of size 2 by 2. Now clearly the number of columns of A is 2 is the same as the number of rows of B. So matrix multiplication, yes, is possible. And what would be the size of this new matrix AB? This new matrix AB, guys, will have size. Remember, you remove the common part, what's left? This 2 will have size 2, which is the number of rows of the first matrix, by the number of columns of the second matrix, which is again 2 by 2 matrix. So we have been able to make the connection that yes, matrix multiplication is possible. And also we have been able to know the size by just looking at what the matrix is given to us. Now let's go ahead and fill up the elements inside this new matrix. Okay, now how do we go about it? What we normally do is, I'm just going to show you once more the same. Suppose this is a new matrix, say C. In order to do that, I'm going to write down the basic, say, subscript elements of this new matrix C. And I'm going to make sure I'm writing down in terms of the ones which is going to make my life easier. C11, 1, 2, C21, that means the second row, the first column, and C22. Okay, what does C11 mean? The subscript will give me all the information. The first subscript tells me which row I have to take, and it was always going to be from the first matrix. So this one says you have to take the first row of the first matrix. So it is 2, 9. This one says the second element in the subscript, in the double subscript I'm talking about, that means you go to the second column and you look at the second matrix, you look at the first column, 6 and 1. So these two together, 2, 9, 6, 1, will give me the element of the first matrix. This is C11. Okay, let's look at C12. Now the double subscript, the very first one, 1, represents you're getting the element from the first row of the first matrix. So you're having 2, 9 here. But 2 in the double subscript represents the second column of the second matrix. So this is 5 and minus 3. So both of them together will give me C1, 2. Similarly, you will do for this one will be C2, 1. That means you're going to the first matrix. Remember the double subscript, the first element in the double subscript is representing the number of rows from the first matrix. So 2 means you're picking up the second row. And that what goes over here. And 6 and 1 means you're picking up the first column of the second matrix. That's here 6 and 1. Similarly, C2, 2. This is C2, 2. And we have already learned that if you have a row vector multiplied to a column vector, what you do is you multiply 2 with 6, 9 with 1, and have an addition in between. So 2 and 6 is 12, 12 plus 9, 21. Then C1, 2 is going to be 2 with negative 5, negative 10 plus 27 gives us 17. Then the second C2, 1, you multiply 1 with 6 minus 2. That 6 minus 2 is a 4. And then the C2, 2 is 1 with negative 5 and minus 2 with 3. So minus 5, minus 6, minus 11. Okay, so I have shown you how to basically play around with this matrix multiplication. So I have written down some matrix multiplication practices for you guys. Compute, now we have done AB. I want you to multiply B times A. Similarly, I would like you to multiply another set of matrices we have. Now here, you have to be careful. These are not the same size matrices. So A is what? A 2 by 2 and B is a 2 by 3. Okay, so when we do a 2 by 2 with a 2 by 3, let's see first matrix multiplication is possible or not. 2 by 2 and 2 by 3. Oh, great. These two are the same. Yes, AB is possible. Your new matrix AB will be 2 by 3. Okay, let's look at B times A. B multiplied to the matrix A. B is the first now. It's 2 by 3 and A is a 2 by 2. What is happening, guys? 3 is not equal to 2. Not possible. So this matrix is not possible. So what you have to do, guys, is just do the matrix multiplication A with B. Okay, and it will be a new matrix of size 2 by 3. Just exactly follow the rules I've done in the previous one. Similarly, I'd like you to practice the slide where here A is a matrix of, what is it? This is a matrix of 1 row, 3 columns. This is a 3 by 3. Clearly, AB matrix multiplication is possible, and this new matrix will be of size 1 by 3. Okay. So all these are practice for you guys. Now B times A. Now B, remember, is a 3 by 3 and A is a 3 by 1. So when you do B times A matrix multiplication, so what you're going to get? You're getting a matrix of size 3 by 1. Okay, this matrix also matrix multiplication is also possible. Now let's look at some few specific properties of matrix multiplication. We have 4 matrices A, B, C, and D. We're going to multiply A with D, A with B, and A with C. So when you multiply A with D, what you get is 0, 0, 0, 0. I would like you guys to do the matrix multiplication as a practice. When you do A with B, you get 3, 4, 6, and 8. And also with A and C, you get 3, 4, 6, and 8. I would recommend check the matrix multiplication. Now, notice some things. Very important here. What does AD telling us? You have two non-zero matrices, but when they multiply, become a zero matrix. So that is a very important property which simply says that two non-zero matrices can become a zero matrix. Remember, if we, in our real number system, like before matrices, if we multiply two elements, we say if A times B is 0, now if A and B are real numbers, then we said one of them had to be 0. Either A is 0 or B is 0. Remember the zero factor property? This zero factor property does not work in matrices, because if you're multiplying two non-zero, it gives me a zero matrix. So a very important concept. Now also look at the another factor. If I'm multiplying two matrices and I'm getting the same answer, so AB, notice here, is the same. So that means, oh, I can cancel it out. But if I cancel the common matrix, is B the same as the matrix C? In other words, is this matrix the same as the? No. So this is another thing. Cancellation laws also do not hold for matrix multiplication. So very important facts of matrix multiplication is that in general, if I multiply A with B, it may or may not be equal to B times A. We have already seen that before in our examples. Second, cancellation laws do not hold for matrix multiplication. That is, if I have two matrices, matrix multiplication the same, having the same common matrix, but B is not equal to C in that example we just did. Now, if a product of two non-zero matrices can become a zero matrix. So this is the zero factor property is not satisfied in the matrix multiplication. Well, I would like you guys to do some practice of these problems, question 1 to 10, in section 2.1 of the book, which is the Lay book, the 5th edition. Thank you.